All right, hi everyone. I'm Jeff Bezanson. I'm going to be talking about some things that are happening in the Julia community and broader world. My colleague Kanno Fisher suggested this sort of made-up word, compilerization, which here's a high-level definition, if you will. This is basically when you didn't think you were developing a programming language, but you find yourself writing a compiler, right? Or alternatively, you thought you were using a library in a certain programming language, but in fact you are using a different programming language, which may be a fact that is hidden from you. And I think this is something that's happening a lot nowadays. We're seeing a lot of compilers. So it used to be there were kind of only a few compilers in the world. Like there was GCC and Javac and ML compiler and that was it. There were like 5 compilers in the world or something. And now everyone is writing compilers. They're just proliferating. I've got a few examples here. There are many more, but like for example, there are several in the Python world, like Numba, numerical, Python optimizer, TensorFlow, PyTorch, compilers for machine learning. There's several more, but I mean, what this comes down to is, you could be, say, programming in Python, and you need to do some numerical stuff, you want to do some machine learning, maybe you want to work on some data frames, and you bring in a few libraries, you could now be using like 4 compilers in your address space, potentially, which is a kind of a crazy thing. Great. So why do I think this is happening? Well, there are a couple phenomena that's causing this. So I think in any modern CS talk, you're required by law to remind everyone that Dennard scaling is over. So we're not getting any more performance. So people are desperate for performance in any other way they can get it. So we're seeing exotic new architectures like Google's TPUs. Interesting because it's, every idea in computer science is very old, right? Of course, and so people proposed kind of array computing architectures at many points in the past, like systolic arrays is a well-known one from the late 70s, where these things, people proposed these architectures and they never really fully took off. And of course, part of the reason was that general purpose computers were getting so much faster at such a high pace, and why bother with a specialized architecture? But now, the time may have finally arrived. We might find ourselves needing to work with increasingly exotic architectures to get performance. And then on the software side, there are also a lot of interesting different kinds of problems coming up where, again, there are topics that in the programming languages world and the computer science world, people have been researching for a long time and doing all kinds of interesting alternative programming models and program transformations. People have been doing them, and for some reason, and most of the time, the world at large was not very interested in those, and now suddenly everyone is interested in them. Like now suddenly all of these things are cool. So it's an interesting time. So this is why we're getting so many compilers now, I think, in some sense. Okay, so what are some problems with this? So I think we have a lot of problems arising from the proliferation of compilers and the great need to write them. And so one issue is the exoticness of the new architectures, right? So at this point, adding a new conventional backend to a compiler is basically trivial, right? And it's because all the traditional architectures like Intel, ARM, and MIPS and what have you, they have a lot of differences, but they're basically the same, right? You do loads and stores and adds and subtracts and branches. It's basically the same kind of architecture, right? So it's not, nowadays you just implement support for it in LLVM or something, and then everybody can compile to it. We know how to do that. But now with the new architectures, that just does not work anymore. What you have is totally, totally different. So you can't just take, whatever your compiler was emitting and just retarget it to something else. It won't work because the set of primitives you have is utterly different. It's at a whole different level of abstraction. So people are writing, instead of reusing like GCC or something, people are writing compilers from the ground up because they see the whole space is different and what they're trying to generate is totally different. But then when you do this, the problem you hit is basically a sort of faithfulness or soundness, which is is the thing going to do what somebody expects? People invest a lot of effort into learning C or Python, and so they think they understand what their program is going to do, but then if another compiler for some different exotic target swoops in and kind of intercepts it, is it going to do what you expect or not? And then similarly, you have a problem with kind of completeness. Very often, you can't run your whole program. Like, for instance, you can't run your whole program on the GPU. And not only you can't, but people don't even want to, right? You don't want to open a socket from a GPU. Like, it's not something you even need or want to do, right? So these are cases where you're actually only needing to run a subset of a language. But what subset works? What am I allowed to do? What am I not allowed to do? Another way to look at the problem is that compilers are very, very powerful. And in a way, it's kind of nice that people are increasingly appreciating the great power of compiler-based techniques, and more people are getting interested in them. But it's almost too powerful. It's almost too much power, right? A compiler, we think of it as something that runs your program, but it's not really, right? It's something that actually replaces your program with a different program, and you hope that they kind of do the same thing, right? It's just let me just take that program and kind of arbitrarily rewrite it for you and run that instead. What could possibly go wrong, right? And the other kind of dangerous thing about the power of compilers is that it's kind of easy to get started, right? You just kind of, you read SICP, and you go, oh, that's cool, I'm going to go write a compiler. And you can just, and you can get started with it fairly easily, but then it's very difficult to perfect. And, do you really want to sign up, to create the next GCC or the next JVM? Like, is that really a project you want to embark on, right? So it's potentially kind of a dangerous thing. And I think the kind of real world evidence of a lot of these phenomena is basically the bugs that you get. So I've got some example bugs that are kind of fun, just to illustrate this. So I've got bugs from GitHub from various projects, and this is not a project or language specific issue. This is an endemic thing that goes on whenever you write these kinds of custom compilers or add-on, ad hoc compilers, whatever you want to call them. So here's an example from Julia. So this is a Julia package, CUDA-native.jl, which is a GPU compiler. Basically, you can give it ordinary Julia code, and it will try to compile it and run it on the GPU. But you get bugs like this. So I will type here. There's a call to broadcast, which is a standard array kind of operation that people do a lot in Julia. And if you do this particular broadcast operation, this simple expression, instead of it working, you get a weird error. It says, unreachable control flow with multiple predecessors is some weird internal compiler error. It just doesn't work, and it's not even clear why. It just sort of blows up randomly. So that kind of thing can happen. Or another example from Numba compiler in Python. So someone has a kind of weird code snippet, which if you run it in normal Python, it works. But if you run it in Numba, you get an error instead. And so this one, I can relate to this a lot because it involves a code path that has a potentially undefined variable on it. I know very well, that accesses to undefined variables or possibly undefined variables are a very rich source of optimizer bugs. I know this as well as anyone, so I can completely sympathize with this. But this is the kind of thing that can happen. Or another kind of thing, someone wrote nested while loops and a break statement. It's just, it's normal code. But if you run it in Numba, it just doesn't work. And these are, I should say that these kinds of bugs they're often they're in the margins, right? These people still use these systems and they get work done with them, and they are effective in practice. Right? People are able to get a lot of value and performance out of these systems, so they're useful. But these bugs are kind of bothersome, right? It's irritating that they're there. It's kind of frustrating. There's another nice example. This is from the Google Tangent project, which is an automatic differentiation tool for Python, where Matt Rocklin points out that so in Python there's a protocol or interface that you can implement to make an object act like an array, like a NumPy array. And for a few of these, if you pass them into this tool, everything works all right. But then he took a different object that implements this protocol and passed it in. It would have worked in Python, but this autodiff tool just blew up on it. So nope, you run into some error. It doesn't work for some reason. So there's this loss of generality. So, again, most people don't need to do probably this exact thing, so it doesn't really stop you from getting work done. It's not a huge problem in practice, but from a more theoretical kind of compiler perspective, it's very irritating because you want everything to just work, right? I don't want, this objects A and B work, but object C, which is supposed to behave the same, suddenly doesn't work. It's just, it's very unsatisfying. So that's the kind of thing I'd like to fix. So I will talk a bit about what we in the Julia world are sort of trying to do to, hopefully, eventually, sort of remedy this situation. Not that we have the solution. We definitely don't have, the big answer. But there are sort of avenues we're exploring to try to kind of improve the situation. And there are basically two general things you can do, which is that one is try to provide some better abstraction than just transforming code. Because processing code representations is actually very hard. Again, it's that kind of seductively easy sort of thing. You think, oh, it's just a grammar of, it's a tree structure, it has a few possible forms, I'll just traverse it and handle everything. What could possibly go wrong, right? And it's just not like that at all, right? Program representations are very, very rich. They're always full of things that you didn't expect, didn't anticipate. It's actually really, really hard to, properly ingest and understand and, correctly compile or transform a full program in some way. It's very hard to get right. So if you can possibly use some higher level of abstraction than that, you'd rather in many cases. And then the other category of thing is just be able to reuse the existing Julia compiler more. Instead of starting with a whole from the ground up compiler effort, is there some way we can extend the current compiler to be able to do what you need? So there are two projects going on that I'm going to explain a bit about how they work to show how some of this works. So the first example is this package Cassette Jael by Jarrett Revels, who's sitting right over there. So he came up with this. This is basically a framework for doing various kinds of non-standard execution code. So this started with a great observation, I think. So when you have a language like Julia or other languages where you can, like Python, where you can overload and intercept operators and that sort of thing, it's tempting to play this game where you kind of define your own custom type, overload all the methods on it, and then kind of intercept everything that happens, and then you can start doing various interesting things with it. The classic example is this really neat trick called dual numbers, which is basically a special type of number you can define, where you just define the typical operations, plus, minus, times, etc., on this special type of number, and it has the property that if you pass it into generic code, expecting some kind of number, it just runs through, and you actually end up getting a derivative instead of just the normal answer. So it's kind of cool, it's kind of magical, and it works sometimes, but the problem is it doesn't quite work. It's so close to working, but it doesn't really quite work. And so, why doesn't it work? And there are a few reasons it doesn't work, but basically the thing that happens is, in a typical program, you will eventually hit something that's not totally generic. Someone will write something in their program, maybe like an explicit type check. Like they will explicitly write, make sure this is of type float64. And at that point, oh, but this isn't a float64, it's a dual number. So then it's gonna barf at that point. And other variations on that theme. So that's very unsatisfying. So Jarrett kind of observed that this is not quite the right abstraction. Like it's not really that I want to run this program on a different data type. I'd be perfectly happy to run it on the same data type. I just want the derivative of it, right? So it's not exactly the right abstraction. So he came up with this abstraction called contextual dispatch, which I will try to explain.
Excuse me, Jeff?
Yeah.
We lost your microphone. Can you check, please, that it's maybe it's turned off? Or yeah, because we can't hear sound for a while.
It's not. Can you hear me now?
No, I don't know.
It's
okay,
still on.
So this one is on. Okay, well, maybe we'll wait for some.
Maybe if I speak louder?
Yeah.
Okay. All right, so Julia is a multiple dispatch language. Every function is a generic function that's overloaded on all arguments. So we're already dispatching on n things. So it's not a big stretch to say, take everything that's dispatching on n things and just add one more or maybe a couple more things that we'll dispatch on. Change everything from dispatching on n things to n plus 1 things. So for instance, a typical Julia definition will say, basically says to the system, here is how you compute the sign function of a double precision float. And the idea here is to be able to extend the parameterization of that to also say, here's how you compute sign of a double on a GPU on a Thursday, et cetera, et cetera, et cetera. So that's the idea. Is so basically what we want to do is sort of go through and add extra parameterization to everything in the program in a systematic way, which then lets you add certain kinds of definitions which I'll illustrate with an example. So a good example of this is memoization. Simon Byrne came up with this example. It's also in the cassette documentation. So this is kind of a program transformation, right? We've got a program which includes some function, and I want you to now go in and memoize that function. So that is, if you don't know what that is, it's to associate a table with it that keeps track of the answers it's returned before, and if you see the same argument again, we'll return the saved answer instead of recomputing it. So what we do is this. So we're going to memoize the fib function. This is the classic example that every textbook uses. I don't think anyone in the world ever memoizes a function other than recursive fib. But it's the standard thing, so that's what I'm going to do. So we have our fib function. We say using cassette, and the first thing we do is declare a context. So we're going to say cassette.context, memoize context. So that means there's going to be this context, and when I'm in this context, things will be memoized in some way. So we make one. We'll make a particular context which has a certain dictionary. So if you wanted to kind of flush the cache and start with a new dictionary, you could make a new context with a new int-to-int dictionary. All right, and now, right, so a typical, in Julia we use a standard f of x function call kind of notation, but it's actually a syntactic illusion, and internally it's actually just a flat tuple of everything, including the function itself. So internally that's just the fib of an int is just the fib function, which is the nominally typed function, the fib function, and an int. So in cassette basically just adds more things to that tuple for every function. So we add this definition, we can say, now in order to execute in the memoize context the fib function of an int, do the following, right? So so that's that memoize context is the extra parameter that we've added. Right, and so the implementation is the next line. So what it says is to execute that, you do a get, which is a hash table operation, which says basically if this argument is in the metadata, return the lookup value for it. If it's not there, return this special overdub instead token. So that's a special type provided by the cassette package, which basically means when you return that value, the cassette machinery will basically look inside the original implementation of the function and execute into it instead of doing whatever you were going to do in here. So it either retrieves the existing value or continues to introspect inside the code. And then we just need one more definition, which is this post hook. So this is another cassette feature. You can add kind of an after, what Klaus might call like an after method, where we say after what you call fib on an int in the memoize context. Please take the result, that's the out argument, is going to be the answer, and store that into the metadata dictionary of this context with the argument as the key. So that's just 2 lines then. We've written those 2 definitions. And then you use this, all you have to do to use it is say overdub, context, fib, and the argument, and it will run that in that context. So then the name cassette, of course, was chosen to enable various nostalgic audio-related puns. So that's where this vocabulary comes from. So, and the cool thing about this is I can use any entry point I want. I could say overdub in context and just call my main function, or any function. So just enter my program through main, and it will. And since you're now in that context, every use of fib will just be memoized by magic, right? So that's pretty cool. So this gives you kind of a family of code transformations where the interface is just writing a couple relatively normal Julia method definitions, right? So the vision of this is this would enable you to have a library that's relatively compact and easy to read that basically gives you like the diff of what's going to happen when I'm on a GPU, right? In the GPU context, here is what's going to happen differently. The sine function will do this, the cosine function will do that, etc. Rather than just having that buried deep in a compiler somewhere where you're never going to know what's going on. It has some more features. You can also change some things that aren't accessible to overloading. So that's another thing that goes wrong with the kind of overloading based approach is that even in languages where most things are overloadable, usually not absolutely everything is overloadable. Like if you have literal data in the program that you want to change. That's, when you encounter a literal in most languages, like a method call doesn't happen, it's just that literal. So if you want to modify those, it can do that. And it also has the ability to kind of add extra metadata to objects, which it will then carry and flow through the program for you which is sort of an alternative to like basically subclassing something and adding more fields. Instead, just say, no, keep executing with that data type, but just keep this metadata along with it. And this is similar to things that I've done before, like aspect-oriented programming is kind of similar, and there's another paper in the Haskell world, compiling to categories, that does a very similar kind of transformation. This is kind of the Julia-flavored version of that in some ways. And so this package exists now, and it works. If you want, you can try the memoize example and many other examples. If you just if you add the cassette package in Julia, you can use this today. So this is fairly far along, although we haven't done everything with it that we want to, but this pretty much works. All right, the kind of next example, I'm going to talk a bit about a very experimental TPU compiler that my colleague Kanno has been working on. So this is, it's the new hardware from Google that a lot of people are excited about, which many people think could significantly accelerate particular machine learning training and inference and potentially other sort of array organized large kinds of computations, doing convolutions and any sorts of very intensive array matrix oriented computations. So this architecture has an unusual instruction set. Well, it has kind of a language that runs on it called XLA. And XLA is basically designed to be a backend for TensorFlow, essentially. And so it's I don't think it's exactly the native hardware instructions that this thing supports. It's not. It's kind of a level of abstraction up from that, but it's sort of the thing that you have available to you to compile to. And it basically consists of high-level array operations. So it does not have your conventional, integer add, store, load kind of. It's not that kind of a back end to target. It's a back end that has things like matrix multiply, right? So that's what you have to target. So yeah, you can't just say, well, make an LVM backend for it and then you're done. Nope, it won't work because those aren't the primitives you'll be generating. So we have this package xla.jl, which is very, very experimental. It's much more experimental even than Cassette, that has an approach for targeting this architecture. And I will try to explain a little bit about how it works. So here's kind of the recipe. And the game here is we want to reuse the existing compiler as much as possible. We don't want to have a totally ground-up approach where we take your program and make a total hash of it and interpret it in some completely non-standard way that's TPU specific and who knows what it's going to do. So we want to be as rigorous as possible in following the semantics of the language as best we can. So this is kind of the recipe that he's implemented for doing this. So I'm going to walk through all of the steps. But basically what you do is first you define the data model, right? So you set up classes for whatever data model the architecture has. Then you define a class for each opcode. So each primitive operation you have available to target. So in this cases, the opcodes are quite interesting. They have a lot of stuff in them, like things like which array dimensions to operate on, what the sizes of the inputs and outputs are all in those instructions. Right, and then you go through and in normal Julia fashion implement methods on one in terms of two. So you implement methods on the target data model in terms of those opcodes. And then optionally you can go on to implement the behavior of those opcodes in the host language, which would give you kind of an emulation. Right, so if you ran it that way, you would just be running CPU-based implementations of all of the opcodes, which gives you kind of an emulator. But you don't have to do that if you just want to run on real hardware. And then the next step is just run the normal Julia optimizer. So that means going through our normal pipeline of lowering the code and removing abstraction overhead as best we can, inlining as much as we can, constant propagating as much as we can, and reusing that whole chain. So to the extent you understand how that works, you'll at least understand part of how this works. And then we'll get something out at the end of the day, and we hope that everything in the resulting optimized IR basically has these XLA opcodes as fully compile time constants. And then we have something we can just very simply one-to-one map, just walking through the IR a statement at a time, just emit whatever's the correct translation of each opcode into the representation the target expects, which is actually, it turns out it uses a protobuf. So there's a protobuf spec for each of these opcodes, and you just send it to the protobuf package, and it sends off the bits that you need. So this is how it all works. So this is what each thing looks like. So first, step one, the data model. So you declare a struct. In this case, it's called XRT array. It's parameterized by an element type and the exact dimensions. So it has to be specialized on a particular size. And n, I think, is the number of dimensions. And it's a subtype of the Julia abstract array type. So it acts like an array. And then the representation is something, but it basically involves something more primitive that's a storage and so on and so on. But the basic idea is you define the data model. So this thing works on arrays, so here you have an array. And then we have the opcodes, so here are just two of them. There are several more, of course, but this is one of them is dot, which is basically a kind of dot product, where it's a general inner product, and it has inside the dimensions that it's going to operate on. And then another one is broadcast, which is basically a way of taking an array and expanding it out to a larger array by repeating elements. So, and then there'll be several more of these, but you define a struct for each one, so you have a representation. And then you write methods. So in this case, I would implement, so here's how to do star of two of these arrays. And so it constructs some description of the dimensions to operate on. I don't know exactly what this representation is, but it's basically describing which dimensions to contract. And it makes the opcode and calls the opcode on the arguments. And so this I haven't implemented that yet, but notice it's sort of two steps, right? It first constructs an opcode object, and then it applies that opcode object to the two arguments, which we haven't implemented yet. But now this is this is kind of the magical part. So now how do we implement that opcode, if you will? So it looks like this, and this is kind of where a lot of the magic is buried. In Julia, this is kind of like the way we sort of overload the parentheses operator, if you will, where you can make any object callable by writing something like this. So you say, so if I have an HLO dot and it has some arguments, do this. And so crucially, first of all, it's marked no inline, because whatever the implementation of this is, we don't want that to end up in the output. We want the output to have this HLO dot thing in that, because the XLA backend is going to intercept that, and it knows what to, how to translate it to the backend. So it has to be no inline, and then the implementation is basically opaque. So execute is a function that's going to have an annotation on it that basically tells our compiler, do not look inside this. This is a black box. Don't optimize or look in here. You can call it at runtime if you want, but do not optimize into it. And then we put a type declaration on it, which is the two colons. And the type declaration calls this function infer RT, which means infer return type, where we give it the types of everything that came in, the opcode that came in, and the types of all the arguments. And it basically implements the type level behavior of this operation in the XLA platform. So it just has to look at all of that information about the operation and figure out the shape and so on of the array that this would produce. And then the idea is that we will be able to partially evaluate that at compile time. So even though we're not going to look inside the execute function, that's a black box, but we put a type declaration on it, which can be partially evaluated by our normal compiler, so that it sort of knows what type that's going to return. And it will just trust us, essentially. And if we actually ran this, and if the type were wrong, we could get a type error at runtime, but we're not actually going to run it usually, so it doesn't really matter. And we just have to kind of trust that it's implemented correctly, of course. And this is nice because often the only reason a standard compiler can't kind of target something like this is that the type level behavior is just a little bit too complicated. You have to do, say, a little bit of arithmetic on the array sizes and dimensions or something, which is often just slightly out of reach of what a standard compiler is willing to do. Some compilers can be coaxed into doing it. If you have some like a very powerful dependently typed language, maybe you can do it. But most standard compilers aren't going to do it. So this gives you kind of a way to hook in and say, hey, you know what? I know what the type level behaviors of all of these are. Just let me implement them. And then this lets you kind of plug it in. And now your compiler can do it. As an example, here's an example input program. I can say function f of a equals a times a dot plus 1. So the dot plus is a broadcasting addition. So that basically means take the 1 and repeat it out to fill the whole same size and shape as a, and then element-wise add them together. So it's just element-wise plus. So we'll do an element-wise plus of a, and then do a matrix multiply with a. So just composing two operations, so sort of the simplest possible non-trivial thing. And then I will call it on, well, I'll start by making a 2x2 random matrix, and then convert that to this XRT array type, and then call my f function on that. So here's the example input, and let's see what happens. So you can run, in Julia, tools exist to basically look at various intermediate stages of the pipeline. So you can look at the compiler's lowered form, you can look at our optimized IR, you can look at the LLVM IR, and you can look at the native code. So if you run that on this, you get something that's kind of like this. So this is just after the standard Julia optimizer has gone through this. And we can see, it's not very easy to read because it's a compiler IR, but it's not too bad either, right? I have the types, the inferred types of everything are in green, and each of these %1s and so on are SSA values. So I can see I have something that says, okay, we can see the top line is taking 1, which is an int64, and it's converting it to a 0-dimensional XRT array. So it's just wrapping it converting it to an array, 0D, because it's just a scalar. And then we do an HLO broadcast, which we can see it has some gunk in there inside the opcode that's telling you about what kind of a broadcast it's doing. And I guess there's the 2 means, I assume it means it's expanding it to 2x2, since that's what it needs to do. So it's going to expand the 1. And then we do a map of plus, right? So this is going to be the element-wise part. It's a map, of course, in the normal functional parlance, which will operate on those. And then we finally do the dot product. So this is just a very nice sequence of XLA operations. And the key part of this is, this is so simple, we could have been tempted to just take that very simple, 2-function call program. Well, I could just traverse through that and output this directly. Like, that wouldn't be that hard. That would be the, couple, days or day or two's project hack of saying, look, I got something working. But that, no, we must not do that, because that's going to be very hard to generalize, right? So that's why we did it in this kind of more rigorous way, where you want to put as much through the standard compiler pipeline as possible. So now at this stage, basically, we really have to just steal the IR from the compiler, and now we interpret it in a non-standard way. But we've gone through all the normal rigors of the inlining and abstraction elimination that Julia normally does. So whatever's in your program, even if it involves other abstractions that you've defined and various other random things, whatever your code does, if we can somehow optimize it down to something simple enough that it looks like this, then you'll be okay to run on a TPU. So that's kind of the hope. And there's a lot of stuff hidden in there. So this depends on, for instance, a lot of constant propagation happening. How much do you need exactly? I don't know. You need to sort of keep propagating constants until it looks good enough, right? And so this is, that's not super satisfying. You can't just neatly write down what is the static analysis that it's doing. It's not a simple, neat thing that fits on a page. So from an aesthetic viewpoint, not very satisfying, but this really is what people are doing nowadays. Like, they're just saying, look, we just need a whole lot of constant propagation to get what we need. So just, tell it to propagate more. And there's a parameter in the compiler, how much constant propagation should I do? And you just kind of keep dialing it up until it works. This is the world we live in nowadays. Like, this is what people need. So that's what we're doing. And I would love to have a better answer for this. Maybe one day we will, but this is kind of how it is. So all right. So after this, we take this IR from the compiler and just walk right through it. Yes. Okay. So I said some of these things already. Kanno also provides an explain function that you can run on this, and it will look through it, and if there's anything that it doesn't know about, it will try to report on what the problem is. Since it's using the normal compiler pipeline, you'll have a lot of source location information in there, which I've edited out because it's just way too big to fit on the slide. But so if it finds something that it's not able to support, it can give you a traceback of exactly where in the program it came from, where in the call stack it was. And as I said, yeah, constant propagation. So I think I said everything on this slide already. Okay. And then this is the next step. You basically, it gets taken by the XLA backend thing and converts. This is the very, very top part of what was basically a protobuf data structure of what this thing comes out to be. And it's just, you don't want to look at that. Do not look at that. This is the part where we've just handed it off, and yeah, you don't want to know, but it becomes something big and complicated at that point. But the net result is this, which is that Jeff Dean at Google tweeted about Julia, which we were very excited about. So we got this result, so that that was already a big success. So this, yeah, there's lots of open questions in this space. So how, one thing I wonder is how much of this can we just move into a standard compiler? For a lot of these kinds of things, even being very involved in the Julia compiler, I'm not even sure if I would want like a TPU backend as part of the normal compiler. I'm not decided on that, right? Even though it's very useful and people really want it. But it's not very general. It doesn't support the whole language. Can we take that on as part of normal compiler development? I'm not sure. So for instance, people have proposed adding a matrix type to LLVM. I'm not sure what the status of the proposal is, but I've heard that's happened. So will that happen? Is LLVM going to pick up these kinds of like matrix shape kinds of things? Are we going to be talking about inner and outer products in LLVM IR? I don't know. That's a very interesting question that's up in the air right now. Another example is that there's a big proposal about adding automatic differentiation to the Swift compiler, which is something they're working on. In our case, we would rather not have autodiff built into the normal compiler. We'd like to be able to do it as a package. But still, it has yet to be seen how well that will work out. How built in are these things going to need to be? I don't know. How many of these architectures are we going to see? Are TPUs going to take off, and there's going to be TPU 2 and TPU 3, and maybe some totally different exotic architecture as well that we'll also have to support. Hopefully it'll be easier that time around, but where is this going to go? I don't know. And in general, this heterogeneous computing thing, it's very worrying, right? We're used to we have the one von Neumann model of a computer architecture, and you can just run anything on it, and it's all very nice. But what do you do when you have devices that can do different things, and you're not just running one program in one place? Is there some way that this can be solved? That everything can just work out nicely? I don't know. I think it's kind of an open problem. So, and that's it. And I have quite a bit of time for questions, I think. So I will take questions.
So I'm going to pass the mic around for anyone that has questions. So.
Hi, great talk. Thank you for those examples. I feel like you ended the talk on a very different note than how you started, because I think you started the talk by giving these definitions of how you end up like accidentally writing a compiler. It's not something you set up to do, but hey, you ended up with a compiler somehow. But I feel like all your examples were of things where it's sort of evident from the beginning that you need a compiler, and then it's a question of how do you build a compiler that's correct or does the right thing. Is that?
Well, I mean, these compilers are kind of accidental in the sense that you weren't trying to make a language or even a new compiler for that language, but you kind of had to. Like all you wanted was for the same thing to run on a TPU, for instance. But
so
you can't get there sort of through the normal compiler. You have to basically like build your own compiler.
So is the problem really that we now have heterogeneous backends and we're trying to take programs already existing or like programs written in existing Julia and just run them on these different backends, or is there another dimension to this problem that I'm not seeing?
Yeah, no, there are multiple things going on actually. There is more than one thing happening. So the heterogeneous computing thing is one example, and then, but more generally, it's the case of so I didn't talk as much about other examples like probabilistic programming or something. But the other examples are other cases where you need to do a program transformation, basically. And this can be seen as one of those, right? We need to, a compilation is one kind of program transformation. But there are multiple things. Heterogeneous computing is one thing, but other kinds of program transformations, even though you're just going to run on a CPU, are kind of not the same thing, but they're sort of tangentially related. Yeah.
You mentioned the word compiling continuations by Kanno and Elliott. The question I had is, his work constructs an IR using category theory. Is there a reason why you did not seek to try to find general enough IR that these backends could be mapped onto? Why did you not take a similar approach?
Well, I mean, in some sense, I guess it maybe is the same approach. I mean, what it is independent of how you talk about it. And category theory is this thing that you can choose to talk in those terms or not. And it's kind of, I think it's sort of happening whether you use that vocabulary for it or not. So I think we just don't use that vocabulary. It's probably the simplest answer. But it has a lot in common with it, but we're just not thinking of it in those exact terms.
With the cassette, do you have a level of modularity? Like, I imagine if I use a library which uses cassette, and I also want to use a cassette, would there be some conflict?
Maybe Jared can answer that. Can you answer that?
Yeah, so that's a really good question, actually, and was, I think, one of the motivators for cassette in the first place was that people who were using existing systems had a lot of composability problems. So the point of basically adding a context type to dispatch in contextually executed code was to resolve those kinds of ambiguity problems. So the point is, yes, if you have basically two different packages that use cassette under the hood, and maybe this isn't even exposed to the user, but they should be able to compose those packages and basically run. Another way of saying this is a program that does a contextual transform is a valid program for a different contextual transform, potentially. There's nothing in cassette that causes a barrier.
So you can basically kind of overlay them.
Yeah.
So
this composability problem is actually inherent to multiple dispatch in a way. If you're just calling a function that depends on more than one type, and you have the option of choosing one method over the other based on the runtime types. If you don't know what the runtime types are in the first place, then you might not have defined a subset of methods that can give you a non-ambiguous solution to know which method to call. This is one of the reasons actually why C++ avoided adding something like multiple dispatch to the language a long time ago. So the point of cassette is you are at the point of invoking the program. You're basically specifying what the ordering is for resolving method ambiguities, because you're saying run this thing within this context regardless of what the argument types are.
It's analogous in Haskell to layering monads. Right. You have to figure out.
Yes.
You have to decide what order to do.
So there's
Exactly.
there's a nesting order of the contexts, which gives you that hierarchy. Yeah.
100%.
So I was wondering if you have any thoughts on the balance between this kind of compilerization and running and domain-specific languages. So in the sense of, are we being sort of seduced by the siren song of generality and trying to write these transformations over general code, whereas in cases maybe the correct answer is, let's actually try and constrain the kind of code we can write so that we can build smaller tools that let us do our work instead of having to do all this kind of stuff that you talked about.
Yeah, that's a very fair question. Yeah, very, very fair point. I mean, I just love generality. That's something I'm hooked on. I'm a lambda calculus kind of person. That's I make no apologies for that, right? But I could be wrong. But I think experience has shown that people very often don't really like those things. I feel like in my just a very fuzzy way. I feel like people always sort of feel more comfortable being in the same language, in the same editor mode, if you will, alongside their normal code, in the same syntax, rather than feeling like they're using some totally different language. But yes, I think it's possible that in some cases maybe that would be a better way to go. I guess it's possible, but I don't want to believe it because yes, I'm an adherent of the Church of Generality for sure. Yeah, you got me.
So I just have a comment to that question because I think it's a very good question to ask. Because Jeff had a bullet point in one of his slides where he's just like, what subset of the language does, whatever my framework support, whatever my framework is. And I think that's the point of when you start to ask that question, you start to ask yourself, like, is Julia, for example, the right target language for the types of things I want to express? And I think maybe the answer is that this has been a thing for a long time, but recent compilers, I think, can really make it fast and easy to do, is to just embed DSLs. And I think Julia is particularly good at this. There are definitely other languages that are really good at this as well. But the question then becomes how to, as Jeff was talking about, how to reuse the existing compiler machinery to kind of solve some of the problems of compiling your DSL. And there's a lot of kind of deep connections between the kinds of things that you in the front end of the Julia language can do with types and the abstract interpretation that the compiler does just to do normal type inference and normal optimization. And if you define, for example, your own set of types, then you can kind of it maybe is an abuse of the compiler, but you can kind of get the compiler via its own abstract interpretation pass to kind of do abstract interpretation for you over the type domain that you defined. And so there's lots of tricks like this, I think, in other languages as well. But I think the Julia world is definitely moving in this direction of like thinking a bit harder about what subset of the language do I support? Do I support a subset of the Julia language, or should I just design a language that features the constraints that I need for my compiler?
Yeah, I think what happens is very often if you start with a DSL initially, it seems totally different and completely alien to a standard language, and you'll get some great speed ups, for instance, right away, which will be very encouraging. But I think as you go, the compiler for it will just more and more resemble a standard compiler, I think, and you'll eventually where I believe you will usually end up is you'll see you're getting closer and closer to a normal compiler, and you'll realize the difference is actually not that much, and maybe a traditional compiler could be made to do the same things. I think that's what tends to happen.
Okay, well, if we have no additional questions, then I think we should thank Jeff once more.